The first time you see it, it looks like a glitch. In the newest Hubble frames of 3 Atlas, taken at the end of November 25, the interstellar comet is a soft, teardrop glow drifting across a field of streaked stars. Long exposures, high sensitivity, a moving target. Everything conspires to turn the background into lines and the comet into a blur. And yet, along the thin sunward structure astronomers call an anti-tail, there is a second brightening. A tiny condensation of light that seems too compact, too sharp to be a random fluctuation. In one stack it's there. In another, processed differently, it almost vanishes. In a third, aligned on the comet's motion, the main nucleus sits at the head of a 60,000-kilometer dust structure, and that small second knot sits behind it, as if trailing in its wake. Some teams describe it as a fragment, a detached piece of the nucleus dragged out by the violence of perihelion. Others see only dust physics, perspective, and the human tendency to find structure where noise is loudest. This is the new footage that has been quietly circulating through observatory mailing lists and press offices. Hubble's late November and early December views of 3 Atlas, taken as the comet climbs back out of the inner solar system. The images are real. The second point of light is real. What it represents is still up for debate. To understand why this matters, you have to rewind a few months. Back in July, while 3I Atlas was still far beyond Mars, a handful of deep, stacked images from ground-based telescopes showed something odd. When observers aligned and co-added dozens of short exposures to boost the comet's signal, some stacks seemed to reveal a faint, point-like source offset from the predicted position of the nucleus by a small but noticeable amount. It was never strong enough to be cataloged as a separate object, never clear enough to be announced as a confirmed fragment. But it was enough to trigger careful checks of the astrometry and quiet questions. Is there a second body traveling with this interstellar visitor? Most of the time, when you stretch data this hard, what you pull up from the noise is just noise. Cosmic rays, hot pixels, the residual imprint of a background star that didn't quite subtract cleanly. Astronomers know that. They live with signal-to-noise ratios and error bars, with the knowledge that the universe at the limit of detection always looks stranger than it is. But when Hubble's November 30 image revealed a long sunward anti-tail and a train of brightness peaks along it, one of those peaks lying where some earlier stacks had hinted at a second object, the old question resurfaced. Is 3 Atlas shedding pieces of itself into interstellar space? Tonight, we're going to move slowly through that question. We're going to follow 3A Atlas from its first faint appearance in archival spacecraft images, through its discovery, past its close brush with the sun, and into the present moment, where a possible fragment glows faintly behind it. And along the way, we'll ask what the data really say, and what they don't. If you enjoy following this kind of unfolding mystery in real time, you can subscribe for more calm, data-driven cosmic documentaries like this one. When 3I Atlas first entered astronomers' awareness, it didn't look like a mystery at all. On 1 July 2025, the Atlas Survey telescope at Rio Hurtado in Chile picked up a new 18th magnitude moving object against the crowded star fields near the border of Serpens Cauda and Sagittarius. The sky there is thick with background stars. Pulling out anything faint and moving is a challenge. But the Atlas pipeline flagged it, measured its motion, and sent the observations to the Minor Planet Center. With only a few measurements, you can't say much about an orbit. With dozens, you can. Within days, follow-up observations from other observatories revealed that this new object was moving much too fast on a path much too open to be bound to the sun. Its orbital eccentricity was around 6.1, not the slight stretch of a normal comet, but a hyperbolic fling. Its incoming speed at infinity, the velocity it would have far from any star's gravity, was about 58 kilometers per second. Numbers like that don't belong to local comets. They belong to visitors from between the stars. And so the new object received a special prefix, 3I. Third Interstellar. The first was One Oumuamua in 2017, a faint, elongated body that never sprouted a visible coma, but behaved as if something was gently pushing on it. The second was 2A Borisov in 2019, a more conventional comet that disintegrated as it passed through the inner solar system. Now, in 2025, 3 Atlas joined them, a genuine comet, active and brightening, on a one-time pass through our neighborhood. What the Atlas team did not know on July 1st was that the comet had already been quietly recorded for weeks. In early August, a team working with NASA's Transiting Exoplanet Survey satellite, TESS, published a preprint. 3I Atlas had been in TESS's wide-field view from 7 May to 2 June 2025. It was too faint to see in any single 200-second exposure. But by shifting and stacking the images along the predicted track of the object, they were able to pull out a faint but real signal. Over those 26 days, the comet brightened from about 20.9 to 19.6 in TESS magnitude, still invisible to casual observation, but clearly rising. And based on its distance at the time, roughly 6.4 astronomical units from the Sun, that brightness implied something important. 3. Atlas was already active, venting volatile ices far beyond the region where water typically drives cometary activity. Other precovery images followed. The Zwicky Transient Facility had captured it in June. The freshly commissioned Vera Rubin Observatory, in its science validation phase, had swept across it. Together with TESS, these early datasets extended the comet's observational arc back into the outer solar system. And they did something else. They anchored its orbit so firmly that the interstellar nature of 3 Atlas was no longer in question. This was not a local body shaken loose from the Oort cloud. It had fallen into the Sun's gravity well from the galaxy itself. From that point, a timeline emerged. After discovery in July, the comet coasted inward. By late August and early September, it was near 3.80, beyond the orbit of Mars, but already clearly active. On 21 October 2025, it slipped into solar conjunction, passing behind the Sun as seen from Earth. 8 days later, on 29 October, it reached perihelion at 1.360, between the orbits of Earth and Mars, traveling at over 68 kilometers per second relative to the Sun. Then it emerged, on a new leg of its hyperbolic path, headed for a closest Earth distance of roughly 1.80, about 170 million miles, on 19 December 25, before fading back into interstellar space. Against this simple arc, every claimed anomaly, every hint of a second object, has to be plotted. And that's where the instruments come in. You can think of the worldwide response to 3I Atlas as a kind of improvised, Earth-sized observatory. Atlas may have found it first, but almost every major facility that could see it has, in some way, turned to look. At the wide field end, there are the survey telescopes, Atlas itself, scanning for moving objects, Pan-STARRS, ZTF, and the Vera Rubin Observatory as it ramps up operations. These instruments provide the backbone of astrometry, precise positions at precise times, which feed into orbit solutions and let mission planners, if they wish, simulate future trajectories with exquisite accuracy. They also provide secular light curves, long records of how the comet's brightness changes over weeks and months. Then there are the giants. In July and August, ground-based telescopes such as Gemini South, the Nordic Optical Telescope, and the Very Large Telescope began collecting time series photometry and spectra. They measured the colors of the coma, finding it slightly red and growing redder as activity increased. They measured polarization, the preferred directions in which the comet's dust scatters sunlight, and found an unusually strong negative polarization at small phase angles, behavior more often associated with the dark complex surfaces of trans-Neptunian objects than with typical inner solar system comets. High above the atmosphere, Hubble took its first detailed images on 21 July 2025. By tracking the comet's motion, it froze 3 Atlas in place while background stars blurred into streaks. The resulting images showed a compact, teardrop-shaped coma with a subtle tail swept away from the Sun. They also set an early upper limit on the nucleus size, no more than about 5.6 kilometers across, and quite possibly much smaller, since the solid core could not be cleanly separated from the surrounding dust. On 6 August, the James Webb Space Telescope brought its near-spec instrument to bear. In infrared light, where molecules vibrate and rotate in ways that imprint distinctive signatures on the spectrum, JUST saw not just a blur of dust, but specific gases. Strong carbon dioxide emission, weaker water and carbon monoxide, traces of carbonyl sulfide, and other volatiles. The picture that emerged was of a nucleus wrapped in a relatively thin crust, rich in cone and other supervolatile ices that begin to sublimate far from the sun. As weeks passed, more instruments joined. SWIFT, in ultraviolet, detected hydroxyl radicals, the decay products of water, and helped estimate a modest water production rate. SPHERIX, an all-sky spectroscopic mission, saw the same strong co-emission that JUST had hinted at. The Very Large Telescope detected cyanide and even neutral nickel in the coma, signatures it shares with many long-period comets from our own Oort cloud. And then, as 3I Atlas rounded the sun, the network expanded beyond Earth. ESA's Jupiter Icy Moons Explorer, JUICE, managed a distant flyby in November, watching from tens of millions of kilometers away as the comet's plasma and dust tails interacted with the solar wind. Mars-orbiting spacecraft and heliophysics missions caught glancing views. Each dataset was narrow, partial, conditioned by instrument limits. Together, they outlined a simple truth. Whatever else 3I Atlas might be, it behaves very much like a comet. To get from images to physics, you need models. That work began as soon as the first detailed data arrived. Hubble's early observations at around 3.80, combined with ground-based photometry, allowed researchers to estimate the rate at which dust was leaving the nucleus. By fitting the brightness and extent of the coma with numerical models, one team derived dust mass loss rates between roughly 6 and 60 kilograms per second, depending on the assumed size of the grains. At the lower end of that range, the comet was shedding the equivalent of a small car every few hours. At the upper end, every few minutes. A separate study, focusing on the first month after discovery, inferred lower dust production rates between about 0.3 and 4 kilograms per second, and found no obvious tail, perhaps because of viewing geometry and the low speed of the largest grains. But even those modest numbers are telling. They imply a steady outflow of material, driven by sunlight, and they set a minimum scale for the engine underneath, a nucleus with enough surface area and enough volatile content to keep feeding jets of dust and gas into space. As JUST, SPHERIX, and VLT spectra accumulated, the composition of those gases came into focus. Compared to many solar system comets, 3 Atlas is rich in carbon dioxide relative to water. ALMA observations have mapped methanol and hydrogen cyanide in the coma, finding that methanol production increases sharply as the comet nears the sun, and that the methanol to HCN production ratio is among the highest ever measured, tens to low hundreds, depending on the date. NASA summaries estimate that methanol accounts for roughly 8% of the volatile emission, a remarkably high fraction for a comet. For astrobiologists, these are not just exotic chemistry notes. Methanol and hydrogen cyanide are key ingredients in many prebiotic reaction pathways. Meanwhile, the comet's rotation revealed itself not through direct imaging of the nucleus, but through the way the coma brightened and dimmed. Time series observations from multiple telescopes, stitched into a combined light curve, showed a repeating pattern. Every 16.16 hours, the brightness rose and fell by a few tenths of a magnitude. At first, some teams interpreted this as the spin of an elongated nucleus, turning more and less reflective area toward us. But the pattern also matched a different picture. Collimated jets, tied to specific active regions on the surface, sweeping through our line of sight as the nucleus rotated, pumping shells of gas and dust outward in pulses. In that interpretation, the heartbeat of 3 Atlas is simply physics. Sunlight falling on volatile-rich patches, driving jets when they face the sun, relaxing when they turn away. The result is a series of expanding shells buried in the coma. Subtle brightness waves that instruments can detect even when the underlying solid body remains unresolved. Not everyone is satisfied with that. Some commentators, most prominently Harvard astronomer Avi Loeb, have argued that the amplitude and regularity of the 16-hour signal combined with the apparent precision of some jet structures, might point to something more exotic, perhaps engineered venting or even propulsion. So far, though, the data that have been released are fully compatible with natural cometary outgassing. No non-random pattern in jet direction, no radio beacon, no unnatural spectral lines have been found. All of this sets the stage for the anomalies. The first is distance. A normal water-dominated comet spends most of its quiet time in the deep freeze. Activity typically ramps up inside about 30 U, when enough solar energy is available to sublimate surface ice. 3. Atlas was clearly active at 6440 in May 2025, when tests recorded it as a weak but steadily brightening source. That points to super-volatile ices, carbon monoxide, carbon dioxide, perhaps others, as the primary drivers of early activity. It also hints at surface layers that have never experienced intense stellar heating before. The second anomaly lies in how its activity, size, and motion fit together. Some Hubble-based estimates suggested a nucleus less than a kilometer in diameter. A later analysis of non-gravitational acceleration, the tiny thrust produced when outgassing acts like a rocket engine, used WST-inferred mass loss rates and the absence of any significant deviation from a purely gravitational orbit to argue for a much larger body, at least 5 kilometers across, and more than 3 grams in mass. Other teams, relying on different assumptions about dust grain sizes and gas flow, arrive at different diameters. The result is not a contradiction so much as a hierarchy of models. Our inferences about the solid core are still entangled with uncertainties in the coma. Non-gravitational acceleration itself is another focal point. In One Oumuamua, a small but real deviation from a gravity-only trajectory rekindled debates about radiation pressure, unusual outgassing, and exotic shapes. For 3I Atlas, the best current analyses of astrometric residuals, the tiny differences between predicted and observed positions, place an upper limit on any such acceleration. If there is an extra push, it is smaller than about 3 astronomical units per day squared, exactly where you might expect it to be for a moderately active, relatively massive comet. Nothing in the trajectory so far demands new physics. Fragmentation is harder. Interstellar comets are fragile. Twai Borisov broke apart after perihelion, shedding chunks that Hubble could resolve. Many long-period comets from our own Oort cloud have done the same, either catastrophically or in stages. Early in its inbound leg, 3 Atlas showed no such behavior. Light curves were smooth aside from the 16-hour modulation. High-resolution images revealed no resolved companions. A recent study of July data in astronomy and astrophysics reported no signs of fragmentation over the month it monitored the comet. But perihelion changes everything. As 3I Atlas swept through its closest approach to the Sun, it experienced rapid heating across its surface, immense thermal gradients between day and night sides, and torques from jets that could spin it up or wobble its rotation. When it emerged from behind the Sun in early November, observers saw a different morphology. A brighter, more extended coma, and a pronounced anti-tail, a narrow structure pointing roughly sunward. An anti-tail is not by itself an anomaly. It's a geometrical effect. Dust shed earlier, in a range of sizes, can be sorted by radiation pressure and orbital dynamics into a sheet or stream that, from our changing vantage point, appears to project toward the Sun. In that sheet, small variations in density can look like knots or condensations. What makes the latest Hubble images so debated is their clarity. In the November 30 frame, the anti-tail stretches for something like 60,000 kilometers, and within it, distinct brightness peaks stand out. One lies at the expected location of the main nucleus, based on astrometry. Another, trailing behind, is close to where some earlier ground-based stacks had hinted at a second point source. One interpretation is conservative. All of these are just regions of enhanced dust density, the natural outcome of jets turning on and off with the comet's rotation, sculpted by gravity and radiation. Another interpretation, pressed by Loeb and a few others, is that the trailing condensation represents a genuine fragment, a piece of the nucleus that separated near perihelion and now follows slightly behind, linked to the main body by a debris stream. The current data can't fully discriminate. No independent orbit has been calculated for a separate object. No clear, repeated astrometric signature of a second nucleus has been published. And yet, that faint second light remains in the images. Real, but ambiguous. If you're looking for more dramatic anomalies, sudden swings in trajectory, delta V that cannot be explained by jets, a train of dozens of discrete, self-gravitating bodies, you won't find them. What you will find, looking across all the datasets, is a comet that is extremely active for its distance, chemically unusual, and large enough that it pushes some of our preconceptions about interstellar debris. That's already plenty strange. So what could 3 Atlas and its possible fragment be? The simplest picture is that of a natural interstellar comet formed around another star billions of years ago, stored in that system's distant reservoir of icy bodies, and eventually ejected into the galaxy by gravitational nudges. Its nucleus is a few kilometers across. Its surface is layered with ices of different volatility, and its interior is porous, perhaps packed with fractal dust aggregates. When it approached our sun, the most volatile ices, carbon monoxide and carbon dioxide, began to sublimate first, driving activity out at 6O and beyond. Closer in, water and other species joined in, and the combination of heating and spin torques fractured the surface, launching clumps of material into space. In that model, a fragment or two is not surprising. The 60,000-kilometer anti-tail becomes a debris stream, dense close to the nucleus and thinned out with distance. A knot along that stream could easily be a larger chunk, tens or hundreds of meters across, unresolved by Hubble, but carrying enough dust and gas to appear as a secondary brightening. If so, that second point of light is simply one more piece of a disintegrating comet. Refinements abound. The high methanol content and the unusual CHO-HCN ratios measured by ALMA suggest that 3I Atlas may have formed in a particularly cold, chemically rich region of its parent system, where complex organics could condense onto grains before they were assembled into a comet. The strong co-emission relative to water hints at formation beyond that system's snow lines, under conditions not common in our own early solar nebula. Its polarimetric properties, similar to those of some distant Kuiper belt objects, point toward a mixture of dark, carbon-rich material and bright ice. There are more speculative ideas. Some researchers have suggested that bodies like 3E Atlas could be natural life seeds, carrying prebiotic molecules between star systems. Methanol, hydrogen cyanide, and water are all part of chemistry that, under the right conditions, can lead to amino acids and nucleobases. An interstellar comet depositing such material on the surface of a young planet is not a proof of panspermia, but it is a plausible contribution to a planet's organic inventory. And then there are the technosignature scenarios. In that space, the comet's rhythmic brightness variations become a possible signal, not just a spin rate. Its chemical profile becomes an engineered exhaust, not just a frozen accident. Jets become thrusters. The lack of large non-gravitational acceleration becomes a constraint on how such a hypothetical engine would be designed, not evidence against its existence. A fragment trailing behind becomes a possible discarded module, not a broken shard. Right now, those ideas are stories layered on top of data, not demanded by it. If 3I Atlas were a spacecraft, you would expect to see thrusting patterns not tied to solar illumination, or coherent radio transmissions, or structural features in high-resolution images that do not match any known natural process. None of those have emerged. The observations we do have are well described by an active, volatile-rich, structurally complex comet experiencing strong heating for the first time. As the comet recedes from the sun, the window for testing these ideas is closing. On 19 December 2025, 3E Atlas will pass its point of closest approach to Earth, at a safe distance of around 1.8 astronomical units. It will never come nearer. Even now, at roughly that distance, it is a dim telescopic object, out of reach of the unaided eye. From here, the story is one of fading. The nucleus cools, volatile production drops, The coma thins, and the dust tails disperse into a diffuse streak along the hyperbolic orbit. In that fading light, there is still work to be done. Hubble and JWST have scheduled additional observations in December and early 2026, aiming to capture the post-perihelion evolution of the coma and tails. ALMA will continue to monitor molecular lines as long as gas production remains detectable, tracking how methanol, hydrogen cyanide, and other species switch off at different heliocentric distances. JUICE will downlink its high-resolution observations over the coming months, potentially resolving structures in the plasma tail that no Earth-based telescope can see. Dynamical modelers are using the refined orbit to trace the comet's trajectory backward through the local standard of rest into the broader galactic context. Preliminary work suggests an origin in either the Milky Way's thin or thick disk, with some analyses favoring an older, thick disk system that could predate our Sun by billions of years. If so, the ice is now sublimating in our sunlight condensed around a different star in a different epoch of the galaxy's history, long before Earth existed. The fragment question, too, may sharpen or blur as more data arrive. If the second point of light maintains a consistent offset from the main nucleus over time, with its own, slightly distinct orbit inferred from repeated measurements, it will solidify the case for genuine splitting. If instead, it diffuses and disappears as the dust sheet evolves, it will slide back into the larger category of anti-tail structure, interesting but not exceptional. Beyond 3E Atlas itself, mission designers are watching closely. The object arrived too soon, and in too challenging a geometry, for any realistic intercept mission to be launched in time. But its passage has catalyzed new studies of how a future spacecraft might rendezvous with the next interstellar visitor, perhaps by loitering in a pre-positioned orbit and using a powerful solar Oberth maneuver to match speeds. The chemistry, rotation, and fragmentation behavior of 3A Atlas are already feeding into those designs. They are the ground truth on what typical interstellar comets might look like. Eventually, though, the ephemeris tables will thin. Observations will stop. 3I Atlas will become just another entry in a database, a set of orbital elements, a few dozen papers, a handful of images showing a diffuse glow and a faint contested second light. When that happens, it will join a very short list. 3 interstellar objects. 3 different personalities. Oumuamua, small, enigmatic, tailless, nudged by forces we still argue about. Borisov, icy, fragile, behaving very much like a scaled-up version of our own long-period comets, and then breaking apart. Atlas, active at great distance, chemically unusual, perhaps more massive than its predecessors, perhaps shedding fragments as it rounds the sun. Each one has expanded our sense of what is possible. Each one has also reminded us how thin the data can be, how much of astrophysics lives at the edge of detection. A second point of light appearing in stacked images, disappearing in others, re-emerging in a Hubble frame tens of thousands of kilometers from the main condensation. These are not the sorts of signs that lend themselves to definitive answers. They are the kinds of hints that force us to examine our methods, our assumptions, and our appetite for mystery. Somewhere beyond the plane of our solar system, 3 Atlas is already on its way out. In a few years, it will be too faint for even our biggest telescopes. In a few centuries, its path will carry it into the dark between the stars, where its coma will be long gone and its nucleus will freeze again, perhaps for billions of years. The dust and gas it left behind here will disperse, a thin, stretched-out thread of material woven into the broader interplanetary medium. We, for our part, will be left with photons and questions. Photons that tell us about CO and water and methanol and cyanide. Photons that trace a 16-hour heartbeat through a rotating jet system. Photons that, when aligned and stacked just right, seem to show a second object appearing again along an anti-tail. It is tempting to demand a final verdict. Fragment or dust knot, natural or artificial, ordinary or extraordinary. But the universe does not owe us clean categories. Sometimes, all we can honestly say is that something passed through our field of view, briefly carrying the chemistry of another star system, behaving mostly as our models predict, and partly as they do not, and that we did our best to measure it while it was here. 3I. Atlas is that kind of visitor. A body from elsewhere, now entangled with our questions. As it recedes, it leaves behind a subtle imprint on our understanding of comet physics, on our expectations for future interstellar objects, and on our sense of how much of the galaxy we can read from a few grains of dust and a few molecules of gas. And somewhere in that imprint, faint but persistent, is the memory of a second point of light that may or may not have been a piece of its heart.